right, hi everybody. We are going to talk about Lewis dot structures. This presentation is actually really long. It's about 27, 28 slides long. I'm not going to go over all of it tonight. I'm just going to go over the Lewis dot structure part of it, which if you're following along in the textbook, it's chapter 8.3. And I really recommend looking at chapter 8.3 because they give you some tips for solving Lewis dot structure problems. And they have several example problems that are super good to look at. So I'm just going to introduce you to it here, and then you can look more in the book, and then you have some practice problems today. All right, so our essential question, how do I predict the shape of a molecule? So we'll start out by talking Lewis dots. LDS use dots to represent valence electrons in bonding. They're based off what's called the octet rule. The octet rule says atoms want 8 valence electrons. That would be to try to be like a noble gas. So the exceptions would be hydrogen and helium, who only want 2 valence electrons. Let's see if I can lower. There we go, my picture, so we can see everything. All right, so to draw a Lewis structure, and this is a really concise way of learning how to draw it. Your book goes into a little bit more detail. It's got like these steps to follow, which are good, except that I think you can get confused. So I would actually look at the practice problems. So they're example problems, and I think they're the best. So how do you draw a Lewis structure? So the first thing you want to do is count up all the valence electrons from around each atom in the molecule. So let's say we're talking H2O. Let's say that's our example. So you look on your periodic table. Hydrogens only have 1 valence electron. Oxygens have 1, 2, 3, 4, 5, 6 valence electrons. So total for H2, there's 2 hydrogens, so that means 2 valence electrons for them, and 6 valence electrons for oxygen. That means that I have 8 valence electrons that I'm going to be working with. Use a pair of electrons to form a bond between each pair of bonded atoms. So I'm going to have an oxygen and I'm going to have 2 hydrogens. And so I know a pair of electrons is going to go between the oxygen and the hydrogen and the other hydrogen and oxygen. And then you arrange the remaining valence electrons to satisfy the octet rule, except hydrogen and helium, which only need 2. So in my example of H2O, let's think that through really quickly. So we have oxygen, and we have 2 that are bonded to hydrogen, and now hydrogen has 2 around it. Hydrogen is satisfied. It is stable. On the other side, we have another hydrogen, and there's 2 bonds there. Hydrogen is satisfied on this side because it has 2 near it. But right now, oxygen has 2 here and 2 here, so that's 4. It needs 8, so it's going to have 2 lone pair electrons above it. And so that's a total of 8 electrons around the outside. If that blew your mind, you're okay. So that's 8 electrons, and then it would be stable. All right, so we're not worrying about Vesper shapes yet. Vesper shapes come in, so knowing the exact shape of the molecule comes in chapter 8.4. So that's the next thing that we're going to look at. But let's try doing H2O. So I just kind of drew out or told you H2O. So I will give you a little secret as far as the Vesper shapes. You're going to find out that water is not actually a straight molecule. It's a bent molecule. You'll learn to predict that soon enough. So what I want you to understand is that in this diagram, we put 2 electrons right here, and they show it with a line. And I mentioned that once before, that on either side of a line, those are the 2 electrons. So we've got this bond is 2 electrons. So right here, we've got 1, 2. Over here, we've got 3, 4. So we've used 4 of our 8 electrons. So we put the other 2 electrons around, paired and around oxygen. And now if you look, hydrogen has 2 electrons near it, these 2. The other hydrogen has 2 electrons near it, these 2. And now oxygen has 8 electrons around it, these 2, these 2, these 2, and these 2. That makes for a stable molecule, and that's how you draw an electron dot structure. So let's try another one. Let's look at NCl3. So what's the name of NCl3, everybody, if you were really going to figure that one out? So nitrogen trichloride. So I'm looking at it right now. I see nitrogen has 1, 2, 3, 4, 5 valence electrons. Chlorine has 7 valence electrons, and there are 3 chlorines. So let's add them all up. 3 times 7 is 21. So we have 21 valence electrons for chlorine. plus the 5 valence electrons from nitrogen. So that means we have 26 valence electrons. They usually say, and they make this tip, I think, in the textbook, if you're trying to figure out which atom goes in the middle, they say that the atom that is furthest to the left on the periodic table, that's my left, right? So we've got N and we've got 3Cl. So the N is the one that's the furthest to the left. So that's going to be the central atom. And then the chlorines are going to go around it. So we're going to start with nitrogen in the middle, and we're going to attach 3 chlorines. So I have nitrogen, and then chlorine, chlorine, chlorine. Now you put a pair of electrons, which you can represent with just a line. So you put a pair of electrons in between each one. So I have used 2, 4, 6 electrons of our 20, what did I say, 26 electrons. So I have 20 electrons left to distribute around the 3 chlorines and the nitrogen. Now they all need 8 electrons around them. So I'm going to start adding pairs of electrons. So I'm going to go around this chlorine over here. I'm going to add 2, 4, 6, and then the next chlorine, 2, 4, 6, and the next chlorine, 2, 4, 6. That was just 18 electrons. And now I'm going to add 2 more to nitrogen. And now nitrogen has 4 pairs of electrons, 8 electrons. And all of the chlorines have those electrons. Let's look at that again. So I'm saying it, but now let's see it as an actual image. So there's our nitrogen. Each chlorine has in the nitrogen and the chlorine are sharing 2 electrons. So that's what the lines represent. That's a bond. It's 2 electrons. So around the nitrogen, I see 1, 2, 3 lines. So that's 6 electrons. And then underneath nitrogen in this diagram, I see a lone pair of electrons. So it has 8 electrons around it. Around each chlorine, I see 2, 4, 6, and then the line represents 2, so 8. Around each one of the chlorines, there are 8 electrons. So in this diagram, everybody has 8 electrons around them because they're sharing some of the electrons. So the shared electrons count. I was trying to think if there was something else I was going to say about that diagram. Can't think of anything else. All right, so now we have carbon dioxide. So which one's going to go in the middle? The one that's further to the left. So carbon is going to be the one that's in the middle, and we're going to put 2 oxygens on either side of it. So now and I forgot to add up all of our valence electrons. So carbon has 4 valence electrons, and each oxygen has 6. So there are 2 oxygens, so 6 times 2 is 12, plus the 4 from carbon. That means we have 16 valence electrons. So now I'm going to put carbon in the middle, and I'm going to put 2 electrons and an oxygen, and 2 electrons and an oxygen. So now I've used 4 electrons, and carbon now has 4 electrons around it. Each one needs 8 electrons. I said we get a total, let's see, it was 6, 12. I should be writing it down because it's hard to do in my head. You should write it down because it's hard to do in your head. So we had 12 plus 4, we had 16 electrons. So carbon dioxide has 16 valence electrons. When I put the carbon across from 2 an oxygen on either side, that uses up 4 of our electrons. So now we're down to 12 electrons left, and we have to distribute those 12 electrons so that everybody has 8 electrons around them. Now I'll give you a hint. This one is pretty complicated. If I take the remaining 12 electrons and I put 2 here by the oxygen, so here's my oxygen, and 2 more by the oxygen, and 2 more by the oxygen. I've done 2, 4, 6, 8 by the oxygen. And on this side, I do 2, 4, 6, 8 on the oxygen. I have used up 16 electrons. So let's take a look. And something didn't go quite right there. Hold on just a second. Let me figure out what I did wrong. Because it does have to be a double bond. Oh, that's what it was. The carbon Sorry, I had to think about that one for a second. The carbon in my little scenario there did not have enough electrons around it. Each of the oxygens had 8 electrons around it, but the carbon was left with only 4 electrons when you drew it with a single bond. So try drawing it with a single bond. Do that right now, like draw it on a piece of paper next to you. So you have C and draw an O across from it and another O across from it. So it looks like this messy drawing right there, okay? And now put the electrons the way I had said, and you'll see what the problem is. We'll try it again. This is my very efficient way of teaching you guys. Okay, so you can see right now I have used up 16 electrons, but what's the problem with carbon? Carbon only has 4 electrons around it right now, 2 shared pairs. That's not enough, so we can't do that. So that doesn't make carbon stable that way. So the way to solve that then is to take two of the pairs of electrons and bring them in and share them with carbon. So now take a look at the real diagram. So the carbon has 8 electrons around it. You remember each line represents 2 electrons, 2 pairs. No, not 2 pairs, a pair, 2 electrons. And now the oxygens have 2, 4, 6, 8 electrons around them. So they are completely satisfied. Doing electron dot structures, you guys, is an enormous amount of trial and error. Trying it, adjusting it, trying it again, moving it around, and then you eventually figure it out. There's not hard and fast rules. So let's try this next one, H2CO. So what's going to be our center molecule? Well, we're going to look for the one that's furthest off to the left. So in this case, it's going to be carbon. Carbon's going to be our center molecule, and we've got 2 hydrogens and 1 oxygen. So if I were you, I would draw it. I should have had extra paper sitting here. If I were you, I'd grab a piece of paper, pause me if you want, and go ahead and draw a carbon bonded to an oxygen bonded to 2 hydrogens. So carbon is in the middle. Start with a diagram like that. Oh, and I forgot to add up our valence electrons again. So let's do that also. We need to know how many we have. So each of the hydrogens has 1. So we've got 2 from the hydrogens. Carbon has 4, so now we're up to 6, and oxygen has 6, so now we're up to 12. We have 12 valence electrons that we have to distribute, 12 valence electrons that we have to distribute around this molecule. So I'm going to start adding them. Right now I notice that carbon has 6, and it's going to need 2 more. So I could put a lone pair. See if I can do that backwards here. I could put a lone pair right here. So maybe I will just to try it. I'm going to put a lone pair of electrons right there. And now I see that carbon is stable. The hydrogens all have 2 electrons. Both have 2 electrons, so they're stable. So now let's see if I can add the final electrons for oxygen to see if this balances out. So how many electrons have I used? Well, I used, it's hard to point on this, you guys. I used 2, 4, 6, 8 of our 12 electrons. I've used 8 of our 12 electrons. So that means that I have 4 left. So I'm going to try drawing 4 more onto the oxygen. So I drew 4 more onto the oxygen. Is my oxygen stable, ladies and gentlemen? I hope that your answer is a big fat no. There are not 8 electrons around that oxygen. So we're going to need to try that again. Notice that the carbon is stable, but the oxygen isn't. There's nothing we can do with the hydrogens. They're stable. They can only have 2. We can't add or subtract from the hydrogens, but I could rearrange some stuff on the carbon. So what if I try a double bond between the carbon and the oxygen? Let's see what happens there. So I'm going to scribble out the 2 electrons that I had under carbon, and I'm going to draw a double bond with the oxygen. So now let's do some math. How many bonds are there? How many electrons, valence electrons, are there around the carbon right now? Well, carbon has 2, 4, 6, 8. There's 4 lines, which represent 2 electrons at a time. So 8 electrons around carbon, and oxygen has 2 lone pair, so 2, 4, and then the double bond is 2, 4 more. So I have everybody is stable in my diagram. And remember, I was only allowed to have 12 electrons. So let's see how many I have. 12 valence electrons. 2, it's so hard to do this backwards. 4, 6, 8, 10, and 12. 12 electrons. I drew it. So we got that one done. And oops, I'll get my picture out of the way. And look at that. We did it perfectly. Okay, let's try the next one. NH2OH. Ooh, that one is going to be a whole lot more complicated. So I'm going to go ahead and take a look and see which one's going to be furthest over. So I see nitrogen is furthest over. So I'm going to write a nitrogen and H2OH. So I'm going to add a hydrogen and a hydrogen and an oxygen and then the hydrogen. So I will tell you when you see this one is written NH2OH, why didn't they just write H3O? And that's because the O and the H are attached to each other. So they separated that H out. It's just a visual for scientists to go, oh yeah, it's not three separate H's, but that H is attached to the O. Just go with me on this for a second. So take a look at the rough draft that I had. So here is that H that I was talking about right there, attached to the O, and then the other H's are attached to the N. So that's how I started. This is my rough draft. Now I need to add up how many valence electrons I get. So nitrogen has 1, 2, 3, 4, 5 valence electrons. Each of the hydrogens, of which there are 3, have 1 valence electron. So now I'm up to 8 valence electrons. I've got 8. And then oxygen has 6. So 8 plus 6 is 14. So I'm going to write down 14. So I have 14 valence electrons that I get to play with. And currently I have used up 2, 4, 6, 8 of the valence electrons. All 3 of my hydrogens are stable. Is that arrow in your way too? Oh, what did I do? I gave away the answers. I didn't mean to do that. What kind of a teacher am I? Okay, so all 3 of my hydrogens are stable currently. Nitrogen and oxygen, however, are not. Nitrogen only has 6 electrons around it, and oxygen has 6 electrons, or has 4 electrons around it. So I need to distribute the remaining, give me a second here, 2, 4, 6, 8. So I just crossed this off right here. I crossed the 14 and I said I have 6 left because I've used 2, 4, 6, 8 electrons already. So I have 6 left. So I'm going to try to distribute 6 lone pairs of electrons. So let's see what I can do. I'm going to try to put 2 more by the nitrogen. So now my nitrogen is stable. Do you see my nitrogen has 8 around it? Okay, the only thing that I have left that's missing electrons is the oxygen, and I have 4 electrons left. Well, that might work out perfectly and a lot easier than I was expecting. So let's take a look. My oxygen is now stable, my nitrogen is now stable, and all 3 of my hydrogens are stable. Let's look at the official diagram and see how we did. Sure enough, perfect. All right, and finally, let's look at the C2H2. This one is a little bit tricky because the C2, there's no, whoops, went going the wrong way. The C2, they're both central atoms. They're both going to be central. So I'm going to draw a line and I'm going to write C, and H on either end. So this is how I'm starting. This is my rough draft right now, and I'm going to add up how many valence electrons I have. So each of the carbons has 4, so I've got 8, and each of the hydrogens has 2, so I get 10 valence electrons. I get 10 valence electrons. I have used up 2, 4, 6 of the valence electrons, so I have 4 left to distribute. Now the hydrogens are already stable. They have 2 electrons around them, so they're already stable. Now I have to figure out what to put around the carbons. The carbons both have only 4 electrons around them. I've only got 4 electrons left, so what if I did this? I want you to see the error of my ways. So that doesn't work because notice each of the carbons only has 6 electrons around it. So I purposely flashed the answer for you, and now I'm going to go ahead and, oops, I'm going the wrong way. I'm going to go ahead and let you take a look at what the right answer is. Notice that we could take these electrons. I'm going to draw this in a really funny way. Watch what I could do. I'm going to scribble out where I wrote them. So I scribbled them out from on top. And now I'm going to put them here like this, just to make a point. So look where I put the electrons this time. So I'm trying to show you that I took those two that were the four that were floating up in the air, and I made them into a triple bond for carbon. I'm going to attach them with a line. And now it looks, now it looks more like what you would expect, that triple bond in the carbon. So now you can see. So let's add them all up. Let's see how many valence electrons I have. So around hydrogen, I've got 2. Around the first carbon, I've got 2 on the left and 3 on the right. I've got 1 on the left, 1 pair, and I have 3 pairs on the right. Gosh, I can't even tell if it's right or left for you guys. Well, whatever. So I've got 8 around each of the carbons, and so this molecule is stable. So like you see, like you've been seeing, it is a trial and error process. Try, make some diagrams, screw around with it, see what you can do. Let me know if you're totally stuck on one, and I can post answers and that kind of thing to your homework tonight. All right, another thing about Lewis dot structures is called resonance bonding. When there is possible that there's more than one valid Lewis structure for certain molecules, and in that circumstance, we would say that they're going to be in resonance. So let me see if I can move this around. So resonant Lewis structures should all be drawn connected by a double arrow. Here's an example. Ozone, normally oxygen is O2, but it is possible for there to be this molecule that's called O3. And what we notice with O3 is that there's this resonance that goes back and forth. Notice what happened to the double bond. It's shifting between one and the other, and both of the structures are adequate. Both of the structures show all of the oxygens having 8 electrons around them, but where the double bond is could be on either the left or the right. This is a 3-dimensional molecule, by the way, so saying left or right is kind of silly, but it resonates between the two, and the reality is that the real structure is sort of a hybrid between these two resonant structures that we drew here. So when there is the possibility of more than one equivalent drawing, then we say that it resonates, and it actually ends up being sort of a modification or a hybridization of the two diagrams. All right, and then dot structures for polyatomic ions are kind of a challenge also. There's a special practice problem. I think I mentioned it in your homework. It's a special practice problem on polyatomic ions on it's problem 8.5 on page 257 to help you with the polyatomic ions. If you're forgetting, which I think is really easy to do, what a polyatomic ion is, that's from this list of common ions. I mean, that's not really where it's from, but that's where you look at them a lot. The list of polyatomic ions is here. Remember, poly means many. And then they're ions because it's a group of atoms joined together that work like a single ion, and they have a charge. And so here's how you draw the dot structures for these polyatomic ions. So the charge changes the number of electrons. So let's say, let's use, I don't remember what the examples are in this, but let's use, what's the one I'm going for? Phosphate. Let's use phosphate. Phosphate is PO4. That's the molecular structure for it, but then it's a -3 charge. So I've been telling you to count up all of your valence electrons, but because it has a -3 charge, you need to add 3 more valence electrons. You add additional electrons. So if it's positive, you subtract from the number of valence electrons that you counted, and if it's negative, if it's got a negative charge, then you add that many more electrons. And then you put brackets around the entire thing with the charge written as a superscript. So let's try a couple of them. These ones are just, and I don't think I have the actual diagrams for these. I should have pulled them off the internet so that you can see them. If we need to pull them off the internet, we can. All right, I want you to pause me right now. I want you to try drawing these on your own. And I will say, let's see, I'm going to show it to you like this. You draw it, when it says the brackets, you draw the brackets like this. So you're going to put NH4, you're going to put that inside the brackets. So you're going to have an N with 4 H's, and you're going to put that inside of the brackets. All right, so the first thing that I'm going to do is I'm going to count up my valence electrons. So nitrogen has 5 valence electrons, and each hydrogen has 1. So that means that I have 9 valence electrons. However, because it's got a +1 charge, that means that one of the valence electrons has been taken away. So we're going to say, and I'm going to double check to make sure I'm doing that right. Yeah, we're going to say that it has, instead of 9, whoops, do you see that I crossed off the 9 and I wrote 8? It has 8 valence electrons. By the way, when I write this number 8 over here, that's just my chicken scratch. That is not an official, you're not officially supposed to write that. I'm just keeping track of how many valence electrons I get. But this number over here, the +1, absolutely has to be written there. So I don't mean to be distracting and writing extraneous numbers that are going to screw you up. But that in that corner, that's the number of valence electrons. All right. So I'm going to write N, and I'm just going to go ahead. I'm going to make that my central molecule, and I'm just going to attach 4 H's to it, and I'm going to see what happens when I do that. So when I do that, I see every hydrogen is happy. It's stable. It's got 2 electrons around it. Oh, and hey, look at that. The nitrogen has 8 electrons around it also. So the nitrogen is also stable. And I've used 8 valence electrons. So bing, 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 all done. That was easier than it could have been. All right, so let's try NO3. So I'm going to make my brackets. I've made my brackets. I'm going to put a -1 outside of my brackets. So there's my there's my -1 outside of the brackets. And then I'm going to count up my valence electrons. So we've got nitrogen has 5, and each of the oxygens, oh, there's lots of electrons here. Each of the oxygens has 6 electrons. So 6 times 3 is 18, plus 5 is 23. So I have 23 valence electrons that I'm working with, but it's a -1 ion. So I'm going to have to add an extra electron to my 23, and so I actually have 24 electrons that I'm working with. Now I'm going to put nitrogen in the middle, and I'm going to surround it with 3 oxygens, and I'm going to see what happens. So nitrogen, oxygen, oxygen, oxygen. This is what I have so far. Nobody is satisfied right now. I don't have 8 electrons around anything. The easy way maybe would be to put 2 dots over the nitrogen, so I could use up 2 of my electrons that way. And right now, oops, can you not see that very well? I'm going to make those darker. Now my nitrogen is stable. So let's see how many of the electrons I've used up. I've used up 2, 4, 6, 8 electrons. So I'm going to subtract that from my electrons over here. So 24 minus 8 leaves me with 16 valence electrons. So now I have 16 more dots that I could distribute around this NO3. So let me see what I can do with that. I'm going to try just putting 6 dots around each of my oxygens to see what happens. So I've put 6 valence electrons around each of my oxygens. But what I see right now, so as it stands, it looks like everybody is stable. But now let's double check. I was allowed to have 24 valence electrons total. Let's see how many valence electrons I actually have. So give me a second to count them. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. Uh-oh. Uh-oh. That's a problem, right? That didn't add up right. So clearly I'm going to need to do something like with a double bond. So let's try a couple options. What if we got rid of the 2 dots over nitrogen and made a double bond with one of the oxygens? Let's just see what happens. So I don't know how that's going to impact things. I'm going to cross that off. I'm going to make a double bond, and I'm going to cross 2 off of the oxygen. So look how I changed the one down at the bottom. So now the nitrogen, how many electrons does the nitrogen have around it? Well, it's got 8. We're good. How many electrons does that bottom oxygen have? Well, it's got 8, so it's good. Let's see how many electrons we used up. How many valence electrons are there? Did I do it right, or do we still have to play around with it? So I'm going to count my valence electrons. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Yay! Did it right. If I'd done it wrong, my next thing I would have tried is having 2 double bonds. So I just would keep playing with it until everybody had the octet rule. So everybody had 8 electrons around them, and we had used up the correct number of valence electrons. Whew. Boy, any questions about that? So here's a summary of Lewis dots. So the strength of the Lewis dot structure is that it's very simple. You can write them down quickly, and it shows all the electrons, not just the bonds. The weakness with it is that there are lots of exceptions. So let me just give you an example. Boron and beryllium tend to form compounds with less than 8 electrons. How annoying is that? Less than 8 valence electrons. And in period 3 and beyond, some atoms will exceed the octet rule. So it is possible to have some atoms that have more than 8 electrons. They can form like 5 bonds around them. So there are exceptions to the rule that make it difficult, but just like the Bohr model of the atom is a great place to start. It's a great teaching tool. Lewis dot structures are a great teaching tool, and then we'll move beyond them. So your assignment now is to take a look at chapter 8.3. I gave you problems from the book. You want to make sure you know how to do all of the problems from the book. And then there is a worksheet that is an actual turn-in formative assignment. And if everybody's crying, I would be happy to post an answer key. I'm not going to post it right away. I want you to struggle with it. I want you to do the hit or miss that I'm doing. I recommend that you don't do it in pen, though. I recommend that you use pencil and paper. Okay, everybody, that is it. We're not going to go any further with the notes. These notes actually go on a lot more. I could give you lots more notes, but we'll start taking those notes on Monday. So we'll stop with Lewis dot structures today. Have a good night.